morning, good morning, good morning.
Well, good morning, class. Sometimes applications in physics and engineering call for finding a vector that is orthogonal to two other vectors in three-dimensional space. Another type of vector multiplication, called the vector cross product, will give us such a vector. So, to define the cross product the hard way, let vector u be u1i plus u2j plus u3k, and vector v be v1i plus v2j plus v3k. The cross product of u and v, notated u cross v like this, u and an x and a v, is the vector. Recall, a dot product, the result of a dot product is a scalar, but the cross product gives us a vector, and here's the vector that it is: u2v3 minus u3v2i minus u1v3 minus u3v1j plus u1v2 minus u2v1k. Wow, is that ever a mouthful? Are we going to memorize this? And the answer is nah, there's an easier way. We can think of it much more simply by thinking of it as the determinant. U cross v is the determinant of the 3 by 3 matrix with I, j, k as row 1, vector u1, u2, u3 as row 2, vector components v1, v2, and v3 as row 3. And so that indeed is a much easier way than trying to think through all this. This is the easy way to find the cross product of a vector. Now technically, to be absolutely correct, a determinant with I, j, and k, no such animal. But this is a great memory device for remembering how to find u cross v. So, here's an example. Find the cross product of vector u, which is 2, negative 1, 1, and vector v, which is negative 2, 3, 4. Okay? And then what is the area of the parallelogram they span? Well, more information about the cross product is coming real soon. But first thing we want to do is find the determinant with I, j, k in the top row, and 2, negative 1, 1, see 2, negative 1, 1 in the second row, and negative 2, 3, 4, negative 2, 3, 4 in the third row. I just let my software calculate it, but look, I'll do at least part of it. It's I times negative 4 minus 3 times its minor, so to speak, then minus j times 8 minus negative 2, so minus 10j, and then plus k times 6 minus negative, actually minus positive 2, so 4. So negative 7i minus 10j plus 4k. Now, here is the cool thing. The area spanned by vector u and v, I mean, they span a parallelogram, right? They span a parallelogram. If I were to add those two vectors, I'd have to use that parallelogram to find the parallelogram, right? But I can, if I could find the area of that parallelogram, that is the length of the cross product vector. So a cross product geometrically is orthogonal to two vectors you're crossing, and it has length equal to the area of the parallelogram that they span. So the length of this vector is the area of the parallelogram that they span. So let's see, the length of this vector would be square root of negative 7 squared plus negative 10 squared plus 4 squared. So that would be the square root of whatever this is. Square root of 165. So it's an amazing thing, the cross product, for two reasons. U, V, and U cross V form a right-hand triple, and U cross V is orthogonal to both U and V. And the second thing is the length of U cross V is the area of the parallelogram that U and V span. So in other words, the area of this parallelogram here is the length of U cross V. pretty cool beans.